Welcome to our deep dive into multiplexing and transmission. In today's digital world, efficiently sending multiple signals over a single communication channel is essential. Multiplexing is the key technology that makes this possible, allowing us to maximize the use of available bandwidth and improve communication efficiency. Whether you're streaming videos, making phone calls, or browsing the web, multiplexing is working behind the scenes. In this video, we'll explore the main types of multiplexing, including frequency division multiplexing and time division multiplexing, and discuss important transmission concepts. Let's start by understanding what multiplexing really means and why it's so crucial in modern communication systems. Multiplexing is a technique used in communication systems to combine multiple signals into one medium or channel. Imagine several conversations happening at once, but instead of needing a separate wire for each, all the conversations are sent together over a single wire. This not only saves resources but also makes the system more efficient. Multiplexing is fundamental in both analog and digital communications, enabling everything from telephone networks to modern internet connections. By sharing the same transmission path, multiplexing helps reduce costs and infrastructure complexity. Next, let's look at the main types of multiplexing used in practice. There are several types of multiplexing, each suited for different scenarios. The two most common are frequency division multiplexing or FDM and time division multiplexing known as TDM. Both methods allow multiple signals to share the same transmission medium, but they do so in different ways. FDM separates signals by frequency, while TDM separates them by time. Understanding the differences between these methods is essential for anyone interested in communication technologies. In the next scenes, we'll break down each type and see how they work in real-world applications. Frequency division multiplexing, or FDM, is a technique where the available bandwidth of a communication channel is divided into multiple frequency bands. Each band carries a separate signal. Think of it like a multi-lane highway where each lane is reserved for a different vehicle, ensuring they don't interfere with each other. FDM is widely used in radio and television broadcasting, as well as in traditional telephone systems. By assigning different frequencies to different signals, FDM allows many conversations or data streams to travel simultaneously without mixing up the information. In frequency division multiplexing, each signal is modulated onto a unique carrier frequency. These carriers are spaced apart so that their signals don't overlap, preventing interference. The combined signals are then transmitted together over the same medium. At the receiving end, filters separate the signals based on their frequencies, allowing each original message to be recovered. This method is especially useful for analog signals and is the backbone of many broadcast and cable systems. FDM's ability to handle multiple signals at once makes it ideal for high-capacity communication channels. You encounter frequency division multiplexing more often than you might think. For example, when you tune your radio to different stations, each station is broadcasting on its own frequency band, thanks to FDM. Similarly, cable television uses FDM to deliver multiple channels over a single cable. Even traditional telephone lines used FDM to carry multiple calls at once. These real-world examples show how FDM efficiently manages multiple signals, making our daily communications seamless and reliable. While FDM is powerful, it does have some limitations. One major challenge is the need for guardbands, small frequency gap between channels to prevent overlap and interference. These guardbands reduce the overall efficiency of the channel. Additionally, FDM is more susceptible to certain types of noise and interference, especially in analog systems. As technology has advanced, digital methods like time division multiplexing have become more popular for many applications. Let's explore how TDM works and why it's often preferred in digital communications. Time division multiplexing, or TDM, is another popular multiplexing technique, especially in digital communication systems. Instead of dividing the channel by frequency, TDM divides it by time. Each signal is assigned a specific time slot in a repeating cycle. During its time slot, a signal can use the entire channel bandwidth. This method is like sharing a single-lane road where each car gets a turn to drive. TDM is widely used in digital telephony and computer networks, providing efficient and organized transmission of multiple data streams. Time division multiplexing, the channel is divided into time slots, and each signal is assigned a slot in a fixed sequence. The signals take turns transmitting their data one after another in rapid succession. Because the switching happens so quickly, it appears as if all signals are being sent simultaneously. At the receiving end, the process is reversed, and each signal is reconstructed from its time slots. TDM is especially effective for digital signals and is the foundation of many modern communication systems, including digital telephony and data networks. TDM is often associated with digital signals. It can also be used with analog signals. In analog TDM, multiple analog signals are sampled and assigned to different time slots. The samples are then transmitted in sequence over the same channel. At the receiving end, the samples are separated and reconstructed into their original analog signals. This approach was used in early telephone systems to carry multiple voice calls over a single line. Analog TDM paved the way for more advanced digital multiplexing techniques used today. Today, time division multiplexing is a cornerstone of digital communication networks. It's used in everything from telephone exchanges to high-speed data links. TDM allows multiple digital signals to share the same physical medium, maximizing efficiency and reducing costs. Technologies like SONET and SDH, which form the backbone of global telecommunications, rely heavily on TDM. By organizing data into precise time slots, TDM ensures that each signal gets its fair share of bandwidth, making modern communication fast and reliable. Both frequency division multiplexing and time division multiplexing are powerful techniques, but they have distinct advantages and disadvantages. FDM is ideal for analog signals and continuous data streams, while TDM excels with digital signals and bursty data. FDM requires careful frequency management to avoid interference, whereas TDM needs precise timing to keep signals organized. The choice between FDM and TDM depends on the specific requirements of the communication system, such as the type of signals, available bandwidth, and desired efficiency. No transmission system is perfect. As signals travel through a communication channel, they can suffer from various impairments that degrade their quality. Transmission impairment refers to any factor that distorts or weakens the signal, making it harder for the receiver to interpret the original message. Common types of impairment include attenuation, noise, distortion, and crosstalk. Understanding these issues is essential for designing robust communication systems that deliver clear and reliable signals. There are several main types of transmission impairment. Attenuation is the gradual loss of signal strength as it travels. Noise refers to unwanted electrical signals that interfere with the original message. Distortion occurs when the signal changes shape, often due to differences in transmission speed for various frequencies. Crosstalk, another common impairment, happens when signals from different channels interfere with each other. Each of these impairments can impact communication quality, and engineers use various techniques to minimize their effects. Crosstalk is a specific type of transmission impairment where a signal transmitted on one channel creates an undesired effect on another channel. This usually happens when wires or channels are placed too closely together, allowing signals to leak from one to another. Crosstalk can cause confusion and errors in communication, especially in systems where multiple signals are transmitted simultaneously. Engineers combat crosstalk by using shielding, proper cable design, and careful channel assignment to keep signals separate and clear. To ensure high-quality communication, it's important to minimize transmission impairments. Techniques include using higher quality cables, applying error correction codes, and implementing proper shielding to prevent crosstalk. Regular maintenance and monitoring of communication systems also help detect and address issues early. By understanding the sources of impairment and applying the right solutions, engineers can maintain clear and reliable signal transmission, even over long distances. Modulation and multiplexing are two fundamental concepts in communication, but they serve different purposes. Modulation involves altering a carrier signal to encode information, making it suitable for transmission over a medium. Multiplexing, on the other hand, is about combining multiple signals for simultaneous transmission. While both techniques are often used together, it's important to understand their distinct roles. Modulation prepares the signal for transmission, while multiplexing maximizes the use of the channel. Modulation is the process of varying a carrier signal's properties, such as amplitude, frequency, or phase, to encode information. This allows the signal to travel efficiently over long distances and through different media. For example, AM and FM radio use different types of modulation to transmit audio signals. Modulation is essential for adapting signals to the characteristics of the transmission medium, ensuring they arrive intact at the receiver. Multiplexing, as we've discussed, is about combining multiple signals for transmission over a single channel. This is achieved by dividing the channel by frequency, time, or other methods, depending on the type of multiplexing used. The main goal is to make the most efficient use of available resources, allowing more data to be sent simultaneously. Multiplexing is a cornerstone of modern communication networks, enabling everything from phone calls to internet traffic. Many communication systems, modulation and multiplexing are used together. For example, in frequency division multiplexing, each signal is first modulated onto a different carrier frequency, and then all the modulated signals are combined for transmission. This synergy allows for efficient and reliable communication, making the most of available bandwidth and ensuring signals can travel long distances without loss of quality. Multiplexing can be applied to both analog and digital signals, but the techniques and challenges differ. Analog multiplexing like FDM is more susceptible to noise and interference, while digital multiplexing such as TDM offers better error correction and signal integrity. As digital technology has advanced, digital multiplexing has become the standard for most modern communication systems, providing higher capacity and reliability. Multiplexing is used in a wide range of applications, from telephone networks and television broadcasting to internet data transmission and satellite communications. By allowing multiple signals to share the same channel, multiplexing increases the efficiency and capacity of communication systems. This technology is essential for meeting the growing demand for high-speed, high-capacity data transmission in our connected world. Telephone networks, multiplexing allows multiple phone calls to be carried over a single physical line. Early systems used analog FDM, while modern systems use digital TDM. This shift has enabled telephone networks to handle more calls with better quality and reliability. Multiplexing is the backbone of both traditional and modern telephony, making global communication possible. Television and radio broadcasting rely heavily on multiplexing. FDM is used to transmit multiple channels over the same frequency spectrum, allowing viewers and listeners to choose from a variety of programs. Digital broadcasting has introduced new multiplexing techniques, further increasing the number of channels and improving quality. Multiplexing ensures efficient use of the broadcast spectrum and delivers diverse content to audiences. Data networks, including the internet, use multiplexing to transmit multiple data streams over shared infrastructure. Techniques like TDM and packet switching allow many users to access the network simultaneously, maximizing efficiency and speed. Multiplexing is essential for supporting the vast amount of data traffic generated by modern applications, from streaming video to cloud computing. Satellites use multiplexing to transmit multiple signals between ground stations in space. FDM and TDM are both used, depending on the type of data and the requirements of the communication link. Multiplexing allows satellites to handle voice, video, and data transmissions simultaneously, making them vital for global communication, navigation, and broadcasting services. Optical fiber networks, multiplexing takes the form of wavelength division multiplexing, or WDM. This technique is similar to FDM but uses different wavelengths of light instead of radio frequencies. WDM allows massive amounts of data to be transmitted over a single fiber, supporting the high-speed internet and data services we rely on every day. Multiplexing in optical networks is a key enabler of modern digital infrastructure. Despite its advantages, multiplexing presents several challenges. Managing interference, maintaining synchronization, and ensuring signal integrity are ongoing concerns. As the number of signals increases, so does the complexity of the system. Engineers must carefully design multiplexing systems to balance efficiency, reliability, and cost. Advances in technology continue to address these challenges, making multiplexing more robust and scalable. Future of multiplexing is bright, with ongoing research focused on increasing capacity, reducing interference, and improving efficiency. Emerging technologies like advanced digital modulation and software-defined networking are pushing the boundaries of what multiplexing can achieve. As our demand for data continues to grow, multiplexing will remain at the heart of communication innovation, enabling faster, more reliable connections worldwide. Security is an important consideration in multiplex systems. With multiple signals sharing the same channel, there's a risk that unauthorized users could intercept or disrupt communication. Encryption, authentication, and secure channel management are essential for protecting data in multiplex networks. As communication systems become more complex, robust security measures are more important than ever. Wireless networks, including cellular and Wi-Fi systems, rely on multiplexing to handle multiple users and data streams. Techniques like FDM and TDM, as well as more advanced methods like code division multiple access (CDMA), enable efficient use of the radio spectrum. Multiplexing ensures that wireless networks can support many users simultaneously, providing fast and reliable connection. Internet of Things connects billions of devices, from smart home gadgets to industrial sensors. Multiplexing is crucial for managing the massive amount of data generated by these devices. By efficiently sharing communication channels, multiplexing enables IoT networks to scale and support diverse applications, from healthcare to transportation. Cloud computing relies on multiplexing to deliver services to millions of users. Data centers use advanced multiplexing techniques to manage network traffic, allocate resources, and ensure reliable service delivery. Multiplexing helps cloud providers maximize efficiency and meet the demands of modern applications, from streaming to big data analytics. Modern transportation systems use multiplexing to manage communication between vehicles, infrastructure, and control centers. By sharing communication channels, multiplexing enables real-time data exchange for traffic management, safety, and navigation. This technology is essential for the development of smart transportation and autonomous vehicles. Healthcare systems use multiplexing to transmit patient data, medical images, and real-time monitoring information. Multiplexing ensures that critical data can be sent quickly and securely, supporting telemedicine, remote diagnostics, and hospital networks. As healthcare becomes more connected, multiplexing will play an even greater role in delivering high-quality care. Financial institutions rely on multiplexing to handle large volumes of transactions and data exchanges. Secure and efficient communication channels are essential for real-time trading, online banking, and fraud detection. Multiplexing helps financial networks operate smoothly, supporting the global economy and ensuring the security of sensitive information. Educational institutions use multiplexing to support online learning, virtual classrooms, and digital resource sharing. By enabling multiple users to access educational content simultaneously, multiplexing makes remote learning more effective and accessible. As education continues to evolve, multiplexing will remain a key technology for connecting students and teachers worldwide. Entertainment industry depends on multiplexing to deliver streaming video, online gaming, and digital media. By efficiently managing bandwidth and supporting multiple users, multiplexing ensures smooth and high-quality experiences for audiences around the world. As demand for digital entertainment grows, multiplexing will continue to play a vital role. Industrial automation systems use multiplexing to coordinate sensors, controllers, and machinery. By sharing communication channels, multiplexing enables real-time monitoring and control, improving efficiency and safety in manufacturing environments. This technology is essential for the development of smart factories and Industry 4.0. Smart home devices, from thermostats to security cameras, rely on multiplexing to communicate over shared networks. Multiplexing allows multiple devices to operate simultaneously, providing seamless automation and control. As smart home technology advances, multiplexing will enable even more connected and intelligent living spaces. Scientific research often involves collecting and transmitting large amounts of data from sensors and instruments. Multiplexing enables researchers to gather data from multiple sources simultaneously, speeding up experiments and improving accuracy. This technology is vital for fields like astronomy, environmental monitoring, and medical research. Emergency services depend on multiplexing to coordinate communication between responders, dispatch centers, and hospitals. By sharing channels, multiplexing ensures that critical information can be transmitted quickly and reliably, supporting effective response and saving lives. This technology is essential for public safety and disaster management. Space missions use multiplexing to transmit data from spacecraft, satellites, and ground stations. By efficiently sharing communication channels, multiplexing enables the transmission of scientific data, images, and telemetry over vast distances. This technology is crucial for exploring our solar system and beyond. Military communication systems use multiplexing to securely transmit voice, data, and video between units and command centers. Multiplexing enhances operational efficiency, security, and coordination, supporting mission-critical operations in challenging environments. Advanced multiplexing techniques help ensure reliable and secure communication under all conditions. To sum up, multiplexing is a foundational technology that enables efficient, reliable, and scalable communication across countless applications. From FDM and TDM to advanced digital techniques, multiplexing maximizes the use of available resources and supports the ever-growing demand for data. Understanding the principles of multiplexing, transmission impairment, and the difference between modulation and multiplexing is essential for anyone interested in communication technology. As we look to the future, multiplexing will continue to drive innovation and connect our world in new and exciting ways.